Hello folks, this is the first tutorial that I'm preparing for the playlist, which is on buckling analysis in the 3D Experience platform. The native FEA solver for the 3D Experience is the ABAQUS program from Simulia, but the interface and some of the functionalities are different from what you may see in the ABAQUS CAE software. The purpose of these tutorials is to provide some assistance to the people who are transitioning from ABAQUS CAE to the 3D Experience version. And that being the case, what I do is I take problems that are available on YouTube and done in a step-by-step fashion in the CAE program, ABAQUS CAE program, and then replicate those steps as needed in the 3D Experience platform. The particular problem that I'm looking at is done by this YouTuber, and it deals with the buckling of a thin can. I think I called it the steel soda can. I think he's calling it beer can, which is fine. Fine, it's the same geometry and same purpose. And I do, however, make a simplification here, and that is I assume that this is a straight cylinder without this top and the bottom indentations, and the bottom is clamped and the top is being pushed down by certain amount. And in order to create the or to mimic uh, the concept of imperfection, this YouTuber is applying a very small lateral force at a middle location. So that's the way he brings uh, imperfection to the picture. Now, what I do is uh, do the problem as a shell problem and create two reference points, reference point 1 and reference point 2, and then create a coupling between the edges, the four edges of this side and this reference point 1, and the other side and reference point 2. Uh, this end is clamped, this reference point is clamped, RP1 is clamped, and RP2 is being axially pushed by 0.5 millimeter. And that the lateral force is applied 1.4 millimeter, 1.4 Newton is applied at that center location. Now, here is the way the tree is going to look like. The coupling is appearing here, and when it comes to coupling, you have to decide what kind of coupling you want. Or you make a kinematic coupling where all 6 degrees of freedom are uh, engaged. Uh, the mesh that you see here is actually a size 9.1 millimeter, but the analysis is going to be done with uh, a tenth of that size. In other words, my analysis, as you'll see, is going to be a lot finer than what you see here. This is only for visual purposes. The dimensions of the can are given as 100 millimeter lengthwise, 33 millimeter radius, and uh, yeah, and the density is 7,800 kilogram per meter cube, which is essentially steel. These are the Young's marginal Poisson ratio for the steel, and the thickness of the can is 0.1 millimeter. Now, in the YouTube analysis with the ABAQUS CAE program, the professor um, uh, does it as a linear or static analysis, static buckling analysis, and then repeats that with a dynamic, implicit dynamic buckling analysis, and that's why you need the density here. However, I have to say a few things about uh, what I get in reference to what he does. In my static run, in other words, just create a static step and apply those conditions that I mentioned to you. And these are the information that I'm going to be using, nothing fancy here. Uh, what you get is a force displacement curve. In other words, that end, RP2, which is being pushed by a half a millimeter, you need a force, of course, to do that. You'll notice that when you do static analysis, or at least that was my experience, you get straight line. Now things go nuts when it reaches roughly 0.15 millimeter, because there is going to be global buckling here. Okay, so I wanted to push it by zero point 0.5, but it doesn't, because the convergence actually stops. There is no convergence when it reaches roughly 0.15 millimeter, and the applied load of about seven kilonewton. Now, uh, by the way, I will show you, as I do this example, I will show you how to create a graph like that. Obviously, you have to do something along this line, but we'll get to that when we do that later. Now, and this is actually uh, the displacement contour, displacement contour uh, in the Z direction, which is actually pattern-wise very close to what the YouTube reference is showing. Now, when I do dynamic analysis, this force displacement curve is obtained, and notice that actually the convergence stops at around 0.15 millimeters. Okay, remember, with static it went all the way to 0.15, but here is point. Let me see. It's let me see for a second. Uh, yeah, 0.15. Okay, but over here, this is before that 0.15 is going to put you somewhere around there. Okay, this actually matches the results of the YouTube channel. Okay, for dynamic analysis, but I do not mine do not agree with what he gets in the static analysis. In fact, let me show you what he gets. For dynamic, you can see that straight line, and then drops at about 0.15, point 1, maybe 0.105 or something like that. Uh, yeah, 0.11. It drops dynamic. In the case of static, he comes up with a dip pretty much at the same location that the dynamic shows a dip, but then it picks up again. So he's referring to this as local buckling, and this is the global buckling. Remember, mine kept going on and on and on until at 0.15 it's pretty much stopped. My global buckling, based on that analysis, the analysis that you see, is going to be right here. So this straight line, no tip here. So I was a bit curious on can I, why is there a difference? So what I decided to do is actually do also a static RIX run. Now, static RIX run is when stiffness is lost, the method will not converge, but uh, RIX method allows you to just uh, go past that. Okay, uh, so of course, when I did this thing and tried to push it by point 0.5, again it stopped after a while. However, this is what I got, and notice that force displacement curve right there, and it matches at this location with the YouTube channel on the ABAQUS CAE. And then local buckling take place and stiffness reduces. So you see that if you look at this location, it's roughly 4.4 kilonewton at this 0.10 something, which agrees with that dip, which I got in the dynamic case, and that gentleman is getting it with the static case. But I cannot get it with the straightforward static. I have to do static RIX run in order to get that. Now, because these things don't, take time, all I do is to show you the steps to do for the static case, okay, which is obviously mine is not matching his result closely. There is no dip test shown, but if you want to do the dynamic or the rig step, then all you have to do, instead of inserting or for procedure selecting static step, you can select implicit dynamics, or you can select as procedure, or you can select the static rig step. Okay, so I'm not going to do that, but that's the only difference. And in fact, if you look at the plot for static rigs run, my static rigs run, which I'm not going to do, it's going to be, as far as the pattern goes, very similar to what the YouTube channel gets. Okay, so that being the case, let's go ahead and get this thing going. I will only do the static case, okay? Because you're dealing with surfaces, so I'm going to go to create my part, not in part design, but I will do that in, for example, generative shape design. I will draw a circle, then extrude it. So on this vertical plane, I will sketch a circle of radius uh, 33 millimeter, because that's what the radius of the can was. Okay, exit, and I'm going to extrude it in both direction, 50 in each direction. So here's extrude, 50 this way, and symmetry, use the symmetric, the mirror option to do it in both sides. Now, let me create my reference point, by the way. So here's a point, and the only things that I said, although it's not relevant, but the position is not relevant, but I will make it 30 millimeter away from this cap. So it's going to 50 plus 30 is 80 millimeter in the X direction. Let's see. Yeah, maybe a little bit more so that I can see it easier. So maybe 100. Okay, good. And then this is this is reference point 1, and do another one. The only difference is minus 100 on the other side. This is going to be reference point 2. Why don't we apply material to this? So it's going to be tools, create a material, just standard steel, standard steel, November 25, 2023. Say okay. Okay, right there. So we're going to apply. Let me close that. Apply to this part. And now we're going to input the values. So let's go here. So structural, because if you're gonna do the dynamic one, you have to specify density. So I might as well put the density here, but I'm not doing that dynamic analysis. So 7800. Remember, if you're doing statics, you don't need this. Try it again. 7800 kilogram per meter cube. Okay. And then ABAQUS multiphysics, mechanical, elasticity, elastic, 208 gigapascal, 208 GPa, and Poisson ratio 0.3. And that's pretty much all we need. Okay, let me do a quick save here. Okay, because I want to apply this sketch, I can hide it actually. Because I want to apply a force here, right there at that location, and I want to have a nice kind of a mesh. What I'm going to do is I'm going to essentially partition this thing, divide it into 8 pieces. But partition, the word partition is used in for solid object, so I'm going to split it. Okay. Uh, yeah, so we don't really have partition for surfaces in the traditional sense. It is really just splitting it and keeping both sides, all sides if you want. So let's go ahead to this, back to this part, and let me see if I can find a split right there. Split, you see that? Okay, so I'm gonna split this, for example, with that horizontal plane. So and keep both sides. Now you can't keep both sides in solids when you split it. That's why they have a different uh, function of facility for that. So one more time. What is that? Split this top with the vertical. Keep both sides. Do the same thing with the bottom. Split the bottom with that plane. Keep both sides. Okay. And I think let me see. I do all of them. It should be 8 pieces. Okay, I have to do it with yeah, the vertical plane. This vertical plane. One more time. Split uh, this one with that, both sides. Split this one with this plane, both sides, and do the bottom ones. Split bottom with that vertical plane, keep both sides, and finally split this plane uh, with that vertical plane and keep both sides. There may be more efficient ways of doing this thing. For example, it may be possible, it is possible to make this solid cylinder, and then you partition it. That you can do, and then extract the 8 faces. Okay, but I didn't go that route. Okay, good. So let's move on. So we're going to go do the meshing. So we go to structural model creation, empty FEM model. Okay. Let's do the very nice rectangular mesh here. So I'm going to do the following: mesh, uh, surface quad mesh on that face. Okay, on that face, and the size here is going to be 0.91 millimeter, just like the YouTube reference is doing. 0.91 mm. Mesh it. You can see very fine mesh. You see that? Very fine mesh. Mine was 10 times bigger. That's why you could see it. Now, say okay. When you do the other one, you have to be careful here. When you do the other one, you should check this box, because there will be duplicate nodes here that unless you check this thing, merge them, they will actually be duplicate nodes. We don't want that. So do this, okay? Uh, and then mesh. And we're going to check and make sure that there are no duplicate nodes. You can see that actually. If I put the cursor there, you can see that uh, at that edge. We're going to check the numbers later on. Okay. Try it again. Keep this box checked. So that one, mesh. Okay. This fellow, mesh. You have to do it on this side. Uh, mesh. Bottom. Oops, I don't think I did that. Okay. And this last one. There are more efficient way of doing this thing, but I'm not worried about it right now. Okay, good, good. So we have 8 surfaces. They're all meshed, and in fact, if you spend some time, let's check that, for example. Okay. At this location, They must have the same numbers, okay? Now, let me put this thing, kind of zoom it in so that I can see it better. To see the element number, node numbers, the easiest way of doing this thing, we go to, first of all, we update everything. Okay, good. So under display, sorry, under view, well, actually, uh, let's see now. We're on node numbering. Okay, let's check this under display right there. Node numbering, element. So this one, notice that there's a node number 1 here. I can see that. If you select the other guy, it's also going to be node number 1. There is nothing overwritten on that node number 1. If you had not captured the mesh the way one way of suggested, then there would have been duplicate node at that location. Okay, good. So I'm done with this. So, all right. Let me put this thing in a view that I can easily see. Okay, cancel. Good. Okay, so we don't want to see the mesh. So let me do visibility. Oh, I forgot to do that, by the way. Yeah, the properties, which I'm going to do that visibility. Let's not look at the mesh. Okay, good. So let's go ahead to the properties and shell properties, and 8 times we have to do this thing. So this, for example, thickness is 0.1 mm, 0.1 mm. Okay. Let's do all of these. Uh, that fellow, 0.1 mm. We did this one, this one, this one, 0.1 mm. It should be so far. Let me see. That's this guy, that guy, this guy. Okay, do another one, which is going to be that, 0.1 mm. Okay, we do it on the other side. Same routine. That fellow, 0.1 mm, 0.1 mm. I could have not done this thing a lot more efficiently, but I didn't want to go that route. So this guy, hopefully I got all 8. If not, it's going to complain later on. We have to come back and fix it. Okay, very good. So let's save. Now we're going to create our couplings. So let's go to the connections. Let me get rid of these tabs. Okay, connections. Here's the coupling. So I want a coupling between this edge, that edge, that guy, and this guy. And for the support 2 is this fellow. That's going to be coupling point 1. And I want kinematic. See that? I used kinematic here. And all of these are checked. And repeat the same thing on the other side. So another coupling between these 4 edges. 1, 2, 3, and 4. And for support 2 is going to be that point. And it's going to be kinematic coupling, all these degrees of freedom. All right, that takes care of this. And as far as the mesh is concerned, we're pretty much done. Let me go to the structural scenario creation. and structural, and the mesh is the one that we just created. Just select it from here, pull down menu. Okay, and we hide these things, hide these elements, right click, mesh visibility manager, and we don't want to see the, yeah, we don't want to see that. Okay, so for procedure, we use static step. If you want to do dynamic, implicit dynamic, you do this, which I'm not doing it. If you want to do static rigs, you do this, okay? But I'm going to do only static step. These are the default values I'm going to take. Remember, I showed you the box for default values right there, okay? And we say okay. Okay, this end is clamped, so we're going to go to boundary conditions. We can either use clamp or say show me all degrees of freedom, fixed displacement. So from here, right click, connections, and from connections, you select coupling 1, and there are other ways of doing it. And all of these are checked. That's what a clamp means. Now for this one, we allow it to actually be actually translated. So what we're going to do is we're going to do again fixed displacement. Once again from here we do connections, and from connections we do this time coupling 2. We take everything except x direction. We check everything except x. That means it is allowed to translate in the x direction. Okay, good. All right, now we're going to apply translation. So that is same place that you got your clamp and you got your fixed displacement, etc. Here apply translation. Once again from the coupling, so we go to connection, see that? You go to connections. From the choice that you've got, you select coupling 2. You say OK, or select. In the direction X, the value is 0.5 millimeter. 0.5 millimeter. Now I can tell you it's going to bomb out at 0.125 because that's where the buckling, global buckling seems to be happening, and it's not going to converge. It's going to go bomb out. So fine. And I want to put a force right at that corner. If I did not have to put the force that right at the corner, I did not even have to split these things. But and there are other ways of doing it without splitting so that you can place a force somewhere there. It includes a point, but I'm not worried about that. So that's why I said there are more efficient ways of doing this thing. But anyway, so we go to load a force at that location right there in the downward direction. Downward direction is minus 1.4 Newton right there. And I think that's pretty much it. So let's save everything and give it a try running it. Okay, so let me unpin this, unpin this. Okay, good. Yeah. So first of all, we do a model check. Good. Then we do a scenario check. Unless I forgot anything, I don't anticipate any problems here. Okay. And finally, we're going to simulate. By the way, I didn't check, but this is S4R, no, S4 not reduce integration, okay? Uh, Four-noded shell, bilinear shell, but doesn't have an R at the end. If you want, you can change it, but it doesn't make a difference in this problem. Okay, so it's going to do the iteration, and I can tell you that when it reaches some point, before I get the 0.5 millimeter displacement, it actually stops, and that's where it detects the buckle. Let's move on. It's going to be very fast. If things don't work out, we can go and change the numbers there. It looks like chuggle, chugging along. It's not very happy. I can see that because you kept getting these U's. U's means didn't converge, but it's not stopping. But at some point, it will stop. Once you get four of these in a row, it will stop. Of course, that can be changed in the settings, but you're not going to do that. Now, notice that point 0.3, you see that point 0.3 times 0.5 millimeter is going to be 0.15, so 0.15-ish. So in fact, you're going to, as you can see, it stops at around 0.15 millimeter. You see, point 0.3, point 0.3, roughly point 0.3. These numbers are getting smaller and smaller and smaller. And I think if you get five of these, it's going to stop. 0.3 times 0.5 millimeter is going to give you 0.15. It's pretty much where I have my graph right there. See that 0.15? See that it's getting smaller and smaller. That point 0.3 is not changing, but these are getting smaller. It's cutting down on the increment. Once it reaches the fifth one, the four unsuccessful one, it's going to stop based on the default settings, unless you change. There, it stopped. Okay, good. Because it stopped, obviously, it's not finished, obviously. And then when you close that, it doesn't show the result. You have to go ask for it. So we go to click on the results right there. Clicked on the results. It says the simulation was terminated before it could complete, of course, because it didn't converge. So you just have the information up to that point. We say close. Okay. So here's the situation. This is before we applied any translation. Now, when you apply the translation, things begin to develop. Let me change this thing to a displacement first, okay. And there, and there, and there, etc. Things are changing, but not much. Okay, now, how do I first of all get get a pattern like that? Because you can see, you can actually see that it doesn't resemble this thing. Excuse me. Excuse me. So what I'm going to do is I'm going to say, fine, let me close that, click on this, XY plot from the field, this thing opens up. Now translation, but I don't want the magnitude. I want downward displacement, direction Z, direction 3, and then say apply. Okay. First of all, this gives you uh, stuff in terms of time. Let me close that. That's really not what I want to do. So let me do the following. Let me double click on this. Yeah, I double click on it, cancel that. I double click on this. This opened up. Magnitude, but I don't want the magnitude. I want direction 3. And then say, okay, there. So when you get the downward displacement, it is acting the way it's supposed to. The only thing is that I want the information. This is all positive and negative displacements. So a couple of things. First of all, let me change the color from smooth to non-smooth. And down here, you see that? It says reverse colors. Okay, reverse colors. You click on, so right now, red is the biggest displacement and blue is the smallest displacement, but they're negative number. But if you say reverse colors, you're gonna get easier to look at and interpret. The other option is to plot only the uh, negative displacements, for example. But this is how I got a plot like that. But the question is, how do I get uh, this kind of a plot? Okay, no problem. Okay, so let me go back here. I'm done with this. So you go to plots, XY plot from the field. We want to generate two plots. One of them is just translation, magnitude of the translation, okay? Which incidentally is going to be, for example, uh, very close to the value translation in the x direction, okay? So let's do the magnitude of the, yeah, let's do magnitude of the magnitude, okay? Magnitude of the translation. And I don't want it at all. I don't want it everywhere, but I want a specific location, namely that coupling point 2, right? So I use the pull down menu. It says node set, and from node set, I don't want all the nodes. I want the coupling to 1, and then we say okay. There. This is the graph of displacement versus time, magnitude of the displacement versus time. Okay. Now I want to do another one, magnitude of force versus time. This is a dummy time, I understand that, but you still have to do something versus time, force versus time, and then plot that something which is displacement against force. So let's do another one. I don't need this, but do another one. Uh, right here, again, XY plot from field. This one I want RF, which is reaction force. For example, magnitude, that's fine. Or I can do direction 1, it's up to you. I don't want everything for the support. I want node set, but not all the nodes. I want, again, coupling to 1, and we say okay. So it's plotted here. So I have now two plots. Let me close that. I have generated two plots right here, XY plots. Okay. Uh, for some reason, I have this one. I don't want. I'll get rid of this. I'll get rid of that. So you can check it. Double click on this. That's the first one. Okay. And this one is, yeah, they're both sitting there because the reason they're sitting there is because I had, yeah, I it was easier if I actually close that. Anyway, I have two plots. One of them is the displacement versus time. The other one is the force versus time. So you click on XY plot from expression. Notice that these are the two plots. That's why I deleted the third one, because it was just inadvertently generated. And then you click on this f of x. See that? This f of x, combine. The combine function appears up here. So I select the first one, and then I select the second one. Let me show you what I did. It's right here. You see that? First as XY plot from field to one for the displacement, the other one for the force, and then from expression, f of x, and combine. That's what this thing is about. And then I say, okay, there we are. This is that plot. Now, I have a feeling that, notice that there's a, let me see for a second. These numbers, let's make sure they match. The height is 7, no problem. But over here, this one is 8. Let me see what that thing is. Yeah, because here I plotted things, not the magnitude of the displacement. I did the displacement in the y direction, sorry, in the x direction. So let me go ahead and redo this. Here, let me get rid of this, get rid of that, get rid of this. Okay, try it again. XY plot from field, translation in the direction vector component 1, 1, that's direction x. Okay, direction x. Translation direction x. Oh, support. Okay, right here. Click, use the pull down menu, node set, coupling to. Let's do it again. We close that. Let's do another one. This one is RF, translation direction 1. So this is the component direction 1. Pull down menu, node set, coupling 2. We say okay. Let me close that. So I have 2 plots here. Okay. So now we go XY plot from expression. Click on f of x. Click on combine. Here is the displacement, and here's the force. And we say okay. And there we are. Yeah, that's a lot better. So 7 kilonewton. This is roughly 0.15-ish, actually, yeah, 0.15-ish millimeter. So what I'm telling you is that this is how I generated. I don't get this. Mine keeps going all the way to 1.15, but I can see something happens if I do it with Rick's method. Okay, so notice that from here to that location, from here to that location is pretty much from here to that location. Something happens, and then it keeps going on. And in fact, the global buckling, if you do Rick's method, where is it? Oh, Rick's method. It also agrees with what the YouTube reference is finding. Okay. Yep. Okay, good luck. So what I did is I did this tutorial, but only use the static analysis, static run. Okay, it's exactly the same story if you do dynamic. The only thing is that when you insert the procedure, don't use static step, use implicit dynamic step. And when you do RICS, just insert a static RICS step. All right, folks, good luck.